The goal of today's discussion is going to be on allylic halogenation, a reaction that involves carbon radicals, similar to some of the concepts we talked about with regard to halogenation of alkanes using free radicals. We're going to be expanding this concept today to talk about allylic halogenation. So in order to understand that, we need to first talk about what we mean when we refer to allylic. The allylic position is defined as the position adjacent to a carbon-carbon double bond. So if we look at the two structures shown on the screen in blue, we should be able to pick out the allylic positions in those as the carbon and corresponding hydrogens adjacent to the carbon-carbon double bond. So if you look, you have the carbon-carbon double bond shown here in red, and then come one spot over via this single bond, and that's going to lead you to the allylic position. So what we're going to see is at the allylic position, we are going to have some special types of reactions take place, and that's why we give it a special name so that we can refer to this position. And the reason that we're going to see some special reactions taking place at the allylic position is because of the fact that we're going to have some resonance that can take place with that carbon-carbon double bond. So the allylic position in the alkene shown on the left is as indicated with the arrow. We can also find the allylic position in this cycloalkene on the right as the position shown with the red arrow here at the bottom. And also there's a second allylic position if we come up here to the top to the 12 o'clock position of that molecule. Those are both allylic positions because if we look relative to the carbon-carbon double bond, we come one spot over, and that's going to be our allylic position that we're going to see is going to participate in some special types of chemical reactions because we can form a particularly stable carbon radical intermediate there, or a carbocation intermediate there for that matter, due to the fact that there's a resonance stabilization from those alkene pi electrons. So let's talk about the reaction of allylic halogenation, which should reiterate some of the concepts that we learned for alkane halogenation reactions. So if we're referring to an allylic halogenation reaction, much like when we talked about alkane halogenation reactions, we need for there to be light and heat present in order to stimulate the formation of radicals. And the specific radical that we're going to be forming here to start with to get the initiation step underway is we're going to be forming chlorine radicals or bromine radicals. And so let's look at an example of an allylic halogenation reaction where we're going to work with the allylic position So the example that we'll target here is we're going to give, for example, and we'll go through the full mechanism for this reaction. We're going to take one butene, like so, and we're going to react it with chlorine, Cl2, at an elevated temperature. So I'm going to put in some light and heat here, and we're going to look at what happens here. Now remember that when we're talking about radical reactions, one of the telltale signs that we should be thinking about a radical is this presence of light and heat. So this is going to be our telltale sign that our reaction should involve a radical intermediate, because if we have a halogen in the presence of light and heat, that's going to suggest to us that we should be thinking about a reaction that involves a radical. And so looking at this reaction in the presence of light and heat, what's going to happen with the chlorine is that that light and heat is going to stimulate the homolytic bond breakage between the two chlorine atoms. And so in the first step of the mechanism, the initiation step as we would call it to get the ball rolling here, in this initiation step, what's going to happen is that the bond between the two chlorine atoms is going to break, homolytically to give 2 chlorine radicals. And remember that we symbolize a radical. A radical by definition has an unpaired electron, so our chlorine radical is going to be Cl dot. So in the initiation step, we can show our chlorine, our Cl2, and we're going to show the homolytic bond breakage between the two. Remember that homolytic means that both of the two atoms are going to get the same number of electrons from the bond breakage. So we show of that covalent bond connecting the 2 chlorines, we use that single-headed arrow, which I've shown, to indicate that one of the 2 electrons from the covalent bond goes onto the chlorine on the right, one of the 2 electrons from the covalent bond goes onto the chlorine on the left. So they're both getting an equal amount of electrons from that bond breakage. That's why we call it a homolytic breakage. And that's going to give us our intermediate that will result from this step. Where our intermediate represents 2 chlorine radicals. And I'm going to show that radical electron in red here for emphasis, because that's going to be the business portion of the molecule. So continuing onward from the initiation step, what's going to happen is that the chlorine radical is relatively unstable, and so they're going to participate in the next step of the mechanism where they are looking for an atom to attack. And this second step we would classify as a propagation step. And in this propagation step, what's going to happen is that the chlorine radical is going to attack a carbon-hydrogen bond to form the most stable intermediate. And this is analogous to what we saw when we were looking at reactions of the alkanes. Remember that with reactions of alkanes, we created the most stable radical by breaking a carbon-hydrogen bond to make a tertiary carbon radical over a secondary and over a primary. In the case of this particular reaction, we're going to be creating a radical at the allylic position, because by creating a radical at the allylic position, what we're going to see is that we will have the opportunity for resonance stabilization. Remember that resonance can be a really strong stabilizing factor in reactive intermediates such as carbocations and also for radicals. So we're going to see that coming into play here with this propagation step, where we're going to use the chlorine radical to basically abstract a proton, or rather abstract a hydrogen via a radical, by breaking a CH bond. And it's going to break that CH bond at the allylic position. The reason it's breaking the CH bond at the allylic position is because that's going to give the most stable intermediate, because it's going to give an intermediate that's stabilized by resonance, rather than with the alkane radicals we talked about. Those were stabilized just by the electron donation of the alkyl groups, whereas here with the allylic position, that's going to be, in general, a better way to stabilize the molecule, because it's going to create a resonance stabilized intermediate. So looking back at our starting material, we started with, as our starting structure here, we started with 1 butene. So we're going to go ahead and copy that down here, our 1 butene molecule. And we're going to show breaking away a carbon-hydrogen bond at the allylic position. So the allylic position is right here, so I'm going to show one of my hydrogen bonds there explicitly so that we can see how it's breaking in this mechanism. Go ahead and finish off the molecule here. And then we're going to put in our chlorine radical that we generated via the first step of the mechanism. And what we're going to see is that we're going to bring together the chlorine radical electron with one of the two electrons from the carbon-hydrogen bond, like so. The two arrowheads, the single-headed arrowheads, indicate that we're moving one electron from each of those atoms as a radical, and the fact that they're meeting up in the middle indicates that we're forming a bond between those two atoms. So in this case, we're forming a bond between H and Cl. We move the other electron from the carbon-hydrogen bond up onto the carbon, and that's going to give us our next intermediate here. So I'm going to scroll down to give us our intermediate that would result from this step of electron pushing arrows. And remember to always use single-headed arrows for these types of processes where we're working with free radicals. So this is going to create for us a resonance stabilized intermediate. And I'm going to put that unpaired electron there on the carbon in red for emphasis. We still have our CH3 group here at the end. And we've also created HCl out of this process, where that bond between the hydrogen and the chlorine was formed via joining the one electron of the carbon-hydrogen bond with the one unpaired electron from the chlorine. So that's going to give us our HCl product here. Now at this point, when we look at the intermediate that we formed here as a result of this propagation step to form our carbon radical, we formed an allylic radical. And the reason that allylic radicals are important and favorable is because they're going to undergo resonance to stabilize them. So the actual structure, the actual electron configuration of this intermediate, the allylic radical, is not going to represent that electron actually being present and stuck on that carbon atom, but instead, by resonance, the actual structure would represent an average or a hybrid, as you might call it, of the possible resonance structures. And so we can look at the possible resonance structures that we can draw here for this, keeping in mind the theme that when we're working with radicals, we're always moving one electron at a time. So this is going to look a little bit different than the previous resonance examples that we've seen in class where we're moving electrons in pairs. Instead, we're going to move one electron, and moving one electron is going to be using a single-headed arrow. So we can move the electron over from the carbon at the allylic position, shown with that unpaired electron in red. Using the arrow that we've shown in blue, we can move that over. However, we're never going to have a single unpaired electron present within a covalent bond. And that's what we're showing based on this arrow. So instead of that being the single isolated process that happens, also what's going to happen is that coming over one position here, we're going to have an electron from the covalent bond coming over, from that pi bond coming over, to make a carbon-carbon double bond here. So we're basically moving an electron from the allylic radical over into the adjacent covalent bond to make the first piece of a pi bond, and then that second piece of the pi bond, the second electron of the pi bond, is going to come from moving over one of the electrons from the alkene group. The other electron from that pi bond, since we said that we can never end up with just one electron present in a covalent bond, that other electron is going to come over and land on the carbon atom here on the far left. That's going to be the only option for it. Any other option would result in exceeding the octet rule, which is something we're never going to do. So the result of these electron pushing arrows is going to be our second possible resonance structure for this molecule, where we're basically sharing the unpaired electron between the carbon on the far left that we're seeing in the second structure here and the carbon number 3 of the chain that we see at the top structure. So that's going to increase the stability of this system. I'm going to show that bond that we moved as blue to emphasize that result of the electron pushing arrows that we showed, and then Go over to the rest of this chain, we're going to be the same. It's always a good idea to check here that we haven't exceeded the octet rule in any case. We can be below the octet rule, remember, but we can never be above the octet rule. So in terms of keeping track of your electrons, it's a good idea to double check that, okay, we haven't exceeded the octet rule in any place. And remember, with resonance, we can't create or destroy atoms, we can only move electrons, so that's exactly what we're doing here. So the actual hybrid structure would represent a weighted average of these two structures, and the advantage of these is that the radical character is split over two atoms, so it's not just stuck on one atom, but due to the fact that we have those pi electrons allylic to the radical, we are able to stabilize this molecule by resonance. And so what's going to happen at the next step is that these radical intermediates are going to react with, in another propagation step, chlorine to form a carbon-chlorine bond at the radical position. And so our second step of the mechanism, or rather our third step of the mechanism, our second propagation step, is that in this second propagation step, we're going to use the unpaired electron from the carbon radical at the allylic position to form a carbon-chlorine bond by attacking another chlorine atom that's present there in the vessel. So in our propagation step here, the carbon radical, which I'll abbreviate as C dot, is going to react with Cl2, and that's going to both yield our final product where we've substituted a hydrogen with a halogen. The other thing that's going to do is that's going to regenerate chlorine radical to go through additional propagation steps. So our two possible scenario here will correspond to our two radicals that we form, our two allylic radicals. So I'm just going to copy those two allylic radicals from up top down here into this step and show the reaction of both of them, and we will get product corresponding to both of these possible structures. So there's one of our structures, and then the other one below it. All right, and bringing in chlorine, Cl2, as our other reactant that's present there in the reaction vessel. Now remember that that bond between the two chlorine atoms is very subject to homolytic breakage. What we'll do is take one of those two electrons from the covalent bond of the chlorine and team it up with the unpaired electron, the free radical from the carbon atom. And when we do that, we have to also take the other electron from that chlorine-chlorine bond and move that somewhere. That's going to go on to the other chlorine to give a chlorine radical product. So looking at the products of this reaction, our organic product of monohalogenation is going to correspond to installing a halogen atom right here, our chlorine atom. Still have 4 carbons on our chain. Now we have the octet rule fulfilled for all of the atoms, so that's good and always a good thing to check. And we've also formed, as a result of this step, chlorine radical. We can do the same process down here with our alternative structure to bring our chlorine atom in on the carbon on the far left. So showing the product of that reaction step. Bringing in that new carbon-chlorine bond here at the end. And then this is also going to leave us with a chlorine radical as well. And the reason that we classify the steps 2 and 3 of the mechanism that we've written as propagation steps is because the chlorine radical that we create here as a result of this final step can re-enter the mechanism at step 2. And that's why we call them propagation steps, because they're basically self-propagating. Once the initiation step takes place, then these 2 propagation steps can continue onward and onward until there's no remaining reactant left in the vessel. So this is going to re-enter the mechanism at step number 2 of that mechanism. And so we can take that chlorine radical that we made as this product of a propagation step, step 3 as we're calling it, and that can re-enter if we scroll back upward. When we go back up to the second step, which we also classify as propagation, notice how there is a chlorine radical reacting there. That chlorine radical can be derived from propagation step that we refer to as step number 3 of the mechanism. And so once the initiation step, which we show up here at the top, has taken place one time in the presence of that light and heat, we're going to see that then the propagation steps can then take off on their own and basically cycle through. So we can cycle through steps 2 and steps 3 of the mechanism with just one initiation step taking place. So as long as we get the ball rolling or initiated by the breakage homolytically of 2 chlorine atoms from one another, then from there the propagation steps can go off on their own to continue to propagate this reaction until essentially there's no reactant left, there's no chlorine left to form a radical, and then we get what we call termination steps, which end the process. But if we're looking at these types of processes, what we're going to see is that these propagation steps are really common. And in the case of the allylic radicals, the key take-home message here is that we're generally going to yield multiple products as a result of these reactions because of the fact that they're resonance stabilized, as we saw here in step 2 of the mechanism, right here as I'm going to circle in green. And that resonance stabilization is going to be one of the factors that favors the formation of a radical at the allylic position, as we see here and also here in green. And additionally, that fact that we have the resonance taking place is going to account for the formation of a couple of different products here corresponding to the 2 electron configurations that we can show for the resonance stabilized intermediates. So let's take a look at another example of this type of scenario of allylic halogenation. And in this particular example, what we're going to look at is an alternative reagent that we can use for free radical allylic halogenation. So chlorine gas or bromine gas can be relatively difficult to handle, and there is in some cases an easier option for carrying out these types of reactions, and that's using a reagent called Inbromo succinimide, NBS for short. So we're going to look at an alternative to using just chlorine or halogen, chlorine or bromine in the reaction, and that is using a reagent called NBS. So NBS stands for Inbromo succinimide. And the structure of NBS is going to basically have a ring where we have a nitrogen directly bonded to a bromine, and then flanking that on both sides is going to be carbonyl group. So this is the structure for NBS, Inbromo succinimide. And the role that this is going to play in the chemical reaction is that we can homolytically break the bond between the nitrogen and bromine. And when that homolytically breaks, what that's going to provide for us is that's going to provide for us a bromine radical. And just as we saw with the scenario of homolytically breaking a bond between two chlorine atoms, or homolytically breaking the bond in Br2 to give bromine radicals, those radicals are relatively reactive and are going to be able to carry out halogenation reactions. And if we think about this scenario of using Inbromo succinimide as our source of radical bromine in a free radical halogenation reaction, we can do an example here where we think about what the carbon radical intermediate that would form would be and what the final product would be. So the example that we're going to look at here is using Inbromo succinimide. The main thing you need to recognize about that is that it's going to be our source of radical bromine. In this example, what we're going to do is we're going to start with our alkene starting material. And I'm going to put NBS as our reactant. And I'm also going to give us some light and heat to trigger and help us form that radical. And I'm also going to throw in some solvent, CH2, Cl2, to facilitate solubilizing both the Inbromo succinimide and our alkene starting material. Remember that CH2, Cl2, also referred to as dichloromethane, and you may see it abbreviated as DCM, is a very common solvent that's used to carry out reactions. So recognize that as our solvent in the reaction, that it's Inbromo succinimide and our alkene starting material that are going to be doing the work. So in this question, what we're going to do is we're going to provide the carbon radical intermediate and we're also going to provide the expected monohalogenation products. So when we say we're referring to the monohalogenation products, we're asking ourselves, if we replaced one of the hydrogens with a halogen, where would we be doing that at? So what's going to be the favored monohalogenation product or products? If we're taking one of the carbon-hydrogen bonds on our starting material and breaking it away and replacing it with a halogen, which position is that going to be favored at? So we can answer that question of what our major monohalogenation product is by thinking about what the carbon radical intermediate will be, because that carbon radical intermediate is going to lead us directly to the final product. And this is really helpful, even if you don't write out a full mechanism for these, to be thinking about where is the carbon radical going to form in the reaction. And so looking at our starting materials here and going back to that concept of allylic radical stability, when we look at this structure, you may be tempted to think, when looking back at the alkane halogenation reactions, that perhaps we need to form a free radical right here at our tertiary carbon, because remember that when we're talking about alkane free radical halogenation, we said that there was a regioselectivity for the reaction occurring at tertiary carbons over secondary and over primary, because tertiary carbon radicals are more stable. However, the resonance stabilization at the allylic position is going to trump the stability that is gained by carrying out the reaction at the tertiary carbon. So the regioselectivity here is going to favor the allylic position being the location where we're going to form that free radical. So you want to be able to recognize the allylic position, and that's going to be a great location to form a radical because we're going to have that resonance stabilization, where the resonance stabilization is going to be greater than the stabilization conferred by having the radical on a tertiary carbon of an alkane group versus a secondary carbon, etc. So our carbon radical intermediate here, in answering the question that we're supposed to answer, and I encourage you to take a moment and pause the presentation and try to write in what you would predict to be the carbon radical intermediate, or intermediates here, to make sure that you're getting this. And then once you've taken a moment and done that, go ahead and unpause the presentation and see what the answer is here that I'm going to put in the box for the radical intermediate, and also take a stab at the monohalogenation product that would result from here. So hopefully you've paused and taken a moment to draw in the radical intermediate here. The radical intermediate that we're going to form, preferentially at the allylic position, is that we're going to have a resonance stabilized intermediate, wherein we'll draw our initial resonance structure corresponding to placing a radical at the allylic position of our starting material. So once we've broken that carbon-hydrogen bond using a mechanism like we saw previously, will give us this allylic radical, and then we can stabilize that by virtue of resonance, and we'll show our electron pushing arrows here to indicate the movement of electrons to give us that resonance stabilization. So we'll move the single electron over from that unpaired electron to make the first portion of this pi bond. The second electron for the pi bond is going to come from the existing pi bond here. So now we've brought 2 electrons in to make a pi bond there. And the other electron from the existing pi bond is going to go onto the carbon on the very end here. So we're basically taking the pi bond electrons, and one of those electrons from the pi bond is going to land on one of the 2 carbons, going away from the other one. And the other electron is going to come over and make that carbon-carbon double bond in this resonance stabilization. So the actual electron configuration of this intermediate would be a hybrid of these 2 resonance structures. And our unpaired electron now is on that carbon on the very end. And if we drew in all the carbons and hydrogens, you would see that the carbon on the end there is going to be a CH2 on the end with the carbon radical. So we're not exceeding the octet rule there or anything like that. So these are going to be our 2 radical intermediates that we would form as a result of this step. And then coming onward from here, we need to think about what our final products are. So these are our intermediates, and then going onward to our final products, we're going to have a few different final products here when we start to think about stereochemistry and keep that in consideration. So for our final products, the final products are going to correspond to bringing in a bromine, because remember NBS stands for Inbromo succinamide, and it's our source of bromine radical. The bromine radical is going to come in and will form a bond between bromine and the carbon radical that we see here in these 2 possible resonance structures. So our final product will correspond to putting a bromine in. Show the bromine in red right there, which would correspond to the resonance structure that we see in the upper left. And then our resonance structure that we see in the lower right is going to give us a different constitutional isomer product. Wherein our bromine comes in and is going to form a bond to the carbon on the very end there. So we do need to think also here about stereochemistry, and we need to think specifically about whether we have formed any chiral centers where we could have the possibility of R and S, and also whether we have formed any EZ stereocenters as a result of these reactions. And in the case where we have indeed, as a result of the reaction, yielded a new stereocenter, we're going to see that we'll observe both the R and the S forms, or in the case of the alkene group, both the E and the Z forms as a result of these reactions. The reason being that with the resonance stabilization and with the carbon radical intermediate being planar, we're going to have no preference for the attack of the bromine from the front side of the molecule versus the back side of the molecule. And so that's going to give us a mixture of the possible stereoisomers there. So we have a few different possibilities that can result from these two structures that we've drawn out so far without too much regard for the stereochemistry of these. And now we need to go in and fill in some stereochemistry, so we make sure that we're actually listing all of the different stereoisomer products that would form here, because we certainly need to be aware of those, since different stereoisomers can have massive impacts on, for instance, the biological functions of these types of molecules. So looking at the structure on the left that we wrote as the final product, when we think about the stereochemistry of this, in looking at the alkene group is at the terminal end there. So if we were to fill in, we would have a CH2 here at the end. We can't assign this as E or Z. There isn't going to be E or Z existing here, because if we look at that CH2 group and we try to assign a higher rank, we're comparing a hydrogen to a hydrogen. Neither of those have a higher rank. They're exactly the same thing. So there is no E or Z here. Don't be fooled into thinking that there's going to be E or Z present there at a carbon-carbon double bond that's at the very end of the molecule. That's not going to happen. On the other hand, though, when we look at the bromine does indeed represent, the carbon there represents a chiral center, because we have 4 different groups bonded to it when we keep in mind that there has to be a hydrogen bonded there as well. So we do need to show the stereochemistry here, and to show the full stereochemistry representation of this using wedges and dashes, what I'm going to do is redraw this to show the R and S enantiomers at that location. So in its full, complete detail, showing the stereochemistry, what I'm going to do is I'm going to show the bromine coming at me as a wedge, and that will give us one of our 2 enantiomers. The other enantiomer, we could envision putting a mirror beside this structure and then drawing the mirror image, or the other way that we can do it is we can imagine making all the dashes wedges at that position and all the wedges dashes at the position. And so in doing that, the bromine, rather than being on a wedge any longer, is going to be on a dash. So we'll go ahead and draw it like this. And if you want to double check your work that you've done this correctly, what we should be able to do is we should be able to go in and systematically assign each of these as R or S using the rules that we learned. So one of these should come up as R, the other should come up as S. If so, we've drawn both of the enantiomers. So we would expect these to be present as a racemic mixture of these 2 enantiomeric products, each featuring that chiral center newly created as a result of this reaction. So that's going to be 2 of our possible products. And then we come over and we look at the other product that we drew out here without too much regard for stereochemistry. And we're also going to see that we have some stereochemistry considerations to make here as well. So we don't have any chiral centers. We have no carbons that have 4 different groups bonded to them. However, what we do have is we do have the possibility for E and Z stereoisomerism, because we have this carbon-carbon double bond here, and at the carbon-carbon double bond we have on one side a hydrogen as well as this 1 carbon chain with a bromine bonded to it. On the other carbon we have a hydrogen and basically a isopropyl group bonded there. So we have 2 possible configurations of this, and so we need to draw those 2 possible configurations, the E and the Z forms, as we could assign them as. So we have this as one possibility, and then the other possibility is instead going to basically put the chain coming downward instead of upward on the right side of that alkene group, or alternatively we could flip the other side as well. But basically we need to take this E form and convert it into the Z form. And there's multiple appropriate ways to go about doing this. One of those ways is like I've shown here. So what we should notice is that if we look at this and we think about E and Z and do our rankings, we'll see that on the right side of the carbon-carbon double bond, the higher ranking group goes upward. On the left side of the carbon-carbon double bond, the higher ranking group goes downward. So if those higher ranking groups are on opposite faces, we refer to the molecule as E. On the other hand, if the higher ranking groups are on the same face of the molecule, we refer to the molecule as Z. So if we've done this correctly, one of these should be E, and the other one that we've just drawn should be Z. So looking at our carbon on the right here, we see that we go down to get to the higher ranking group. If we come over to the carbon on the left, we see that we also go down to get to the higher ranking group. So both of those are down relative to the carbon-carbon double bond. So we would refer to that as being Z. So that's going to be our E and Z diastereomers. So as a result of this reaction where we started with just a single alkene starting material treated with NBS in the presence of heat or light, we get the resonance stabilized intermediates, and then that's going to lead us ultimately to two different constitutional isomer products, where the constitutional isomer products are ones that have a different skeleton. They would have different IUPAC names, such as the two structures that we've outlined in the blue boxes here. And then each of those structures also have some unique stereochemistry that we need to consider as well. And so ultimately we're going to have a total of, to get full credit on something like this, you would need to show all four of these possible structures if you're asked to provide the products of the reaction, including stereochemistry. We're going to observe four possible products of these reactions, where the two structures that we see on the left that I'm outlining in purple are related to one another as enantiomers. The two structures on the right that I'm showing in light blue are related to one another as diastereomers of each other. And so this is going to be the full set of products that we get from this reaction. And the fact that we're getting these different constitutional isomers, that is the structures on the left in purple compared to the structures on the right in blue being constitutional isomers of one another, that is going to result from the fact that we have that resonance stabilized intermediate. And that's something that's going to differentiate allylic halogenation reactions from the alkane halogenation reactions that we talked about in a previous class. So with that, we'll conclude and continue next time with additional reactions of free radical based halogenation.